Hello and welcome to the MicroTAS workshop W4 about control of surface chemistry and wetting. My name is Stefano Begolo and today I'll be talking about wetting and surface energy in microfluidics. Today we're going to cover the following topics. We're going to start with an introduction and basic principles about wetting. We're going to look at wetting and capillary effects and how they apply in microfluidics, specifically for some applications. We're going to then talk about how we can control the surface energy, what are the strategies of there, and how do these strategies can scale for high volume. We're going to wrap up with conclusions and then the following steps that will allow us to keep in contact. A little bit about me. As you can probably tell from my name and accent, I'm from Italy originally. I spent the first part of my career working in academia by going through multiple projects related to the use of surface coatings, biphasic fluids with droplets and slip chip applications, with mostly focus on the portable diagnostics and diagnostic tools in life sciences. Since 2015, I've been working in the industry side, managing a team of engineers at ALine Inc., which is a company that focuses on design and manufacturing of microfluidic devices. But I've kept collaborations going, and I'm very happy to be able to give you this talk today because I think it's a good opportunity for us to keep in touch with the academic world. Let's get into the material then. The first thing I want to go over is the introduction and some basic principles. So you're probably familiar with some hydrophilic effects from your day-to-day lives. So you can see here on the top, this is unfortunately a tool that a lot of us have used in the past 2 or 3 years for testing ourselves. And the main principle about driving fluid into a lateral flow strip is hydrophilic wicking that is used for the lateral flow assays. This is also something you can see when capillary rise, when you have a glass capillary or tube where you see the water actually rising way past the gravity. This is driven by Euler's law, and it's really driven by the contact angle and the surface properties of the capillary. A third example of a hydrophilic effect is when we think about liquid coatings on surfaces. Well, the first things you can think about is painting. And so paint has been optimized and the composition has been defined so that it can spread very easily onto the surface and that will not bead up or create anything that is an unhomogeneous coating. On the other hand, there are a lot of examples of hydrophobic effects in nature. So you can look at here on the top, we have some examples of water repellent coating for glass, for like windshields of our car, for fabric to make sure our clothes don't get wet. A similar effect due to the capillarity is these water striders, so small animals that are actually able to walk on water, or a needle that can float on the water. These are all examples on where the surfaces themselves are, there is some type of hydrophobic surface and some capillary force that keeps these effects in place. And one of the most famous effects that are related to superhydrophobicity is the lotus effect. Some leaves in nature that have this ability to repel water by making themselves very hydrophobic, so that the droplet actually roll over and out from the surface. All of these effects are actually driven by surface energy. So to simplify it a little bit, we got to think about cohesive forces in a liquid or in a material. When a molecule is sitting within the liquid or within the phase, it typically has cohesive force in all directions, and this is the most stable situation for it. On the other hand, when a molecule is sitting on the surface, it still has some cohesive forces, typically on half or less of the sides, but then it loses some of these cohesive forces on the side that is actually facing outside. And so what this makes it happen is that it creates a net pressure at the interfaces that is defined by the Young-Laplace equation, which is defined by this pressure is defined by the surface tension, surface energy, which is an energy that is associated with this interface, and then it depends on the radii of curvature. And the reason why curvature is very important is the reason why droplets tend to be round, because we want to minimize the total surface, and as you know, the sphere is the minimal surface for a given volume. So once we know that there is surface energy associated with it, we can look into the next stage. How do we quantify surface energy and how do we measure it? So the first thing I want to introduce here is the concept of contact angles. Whenever we have an interface between three phases, liquid, solid, and vapor or gas, its stable situation is driven by thermodynamic equilibrium between the surface energies. And so in this case, we have Young's equation that really drives the show. And so you have the three surface energies and this angle theta here that is really defining, that is used as a unit of measure or of the effect of these surface energies. So whenever we're trying to characterize the wetting properties of a surface, we typically use the water contact angle measurements, which is typically used as a sessile drop. We use a small droplets of DI water placed on the surface. It's typically 3 to 5 microliters. The reason for that is to avoid gravity effect. We then, after it's deposited there, an image is taken from the side using the right lighting to ensure that there is good enough contrast. And then typically this is done within a dedicated instrument that's called a goniometer. And then we use image processing and fitting to basically extrapolate the baseline and the shape of the droplet and quantify what is the contact angle, which is basically the angle between the interface and between the three interfaces here. This contact angle measurement is really important because it allows us to classify surfaces depending on their wetting properties. So if the contact angle is below 90 degrees, a surface is typically defined as hydrophilic. Water will tend to spread on it, and typically the droplet shape would be what you will probably expect from a standard windshield of your car, with the droplet streaking and creating a larger surface area. If the surface is above 90 degrees, you typically classify the surface as hydrophobic. This is an example of the standard grass or leaves from plants, where the droplet tends to be mostly round, but it's still staying there and it's typically stuck on the surface. An extreme case is when you add extra roughness to a hydrophobic surface, you get the super hydrophobic effect, which is the one shown here on the right, which, as I said, can be exhibited by lotus, ginkgo biloba, or other plants, where the droplet contact is so small that by gravity it just rolls over, and you're not even able to stabilize it to measure a defined contact angle. It gets very tricky. One thing to keep in mind is that all of this classification is really driven by a static effect, when the droplet is at the equilibrium and it's all measured in a static condition. Once we start looking at dynamic effect, which is what we like to do in microfluidics, we want to move fluids around, we don't want to just get them to stay stuck, there are some other effects that take into place that are called contact angle hysteresis. What happens is that if you take a droplet and you tilt it, your droplet will move, but the contact angle will be different between the front and the back. Same way, if you're taking a droplet and you're adding or removing liquid, you might end up with contact angles that change depending on the amount of volume that is included. The reason for this happening is what we call pinning or contact lines. So whenever you have surface heterogeneities, can be chemical or physical, they tend to lock the contact line in place, and that creates the hysteresis because it's really a dynamic effect where if you're pulling and your line stays back, you're going to have a smaller contact angle here and a larger contact angle in the surface. And so this is typically driven by, depending on the molecule itself, it can be driven by surface roughness, by chemical heterogeneities, that's something that can be diluted inside of the droplet, or a variety of components. But the key take-home message here is that the heterogeneity drives capillary effects in real life. You're rarely going to get into the stage of going back to the contact angle equilibrium. You're always going to have to deal with imperfections getting in the way and potentially influencing the results of what you're looking at. We now move into some examples of wetting and capillary effect on the microfluidic application, which is, I think I felt it was good to go about specific examples rather than staying just on the theory side. The first thing we're going to start with is hydrophilic effect again. So you're probably familiar with some of these examples. I just took a few, just a representative, but one example is the use of 2D paper networks that has been like shown in the example here is shown by Paul Jaeger's work at UW. Similar things have been done by many other groups, but I'm just using this as a representation. In this case, we are using paper that is basically a porous hydrophilic material, and we are using wicking and the contact angle of the paper being like very hydrophilic to drive the loading of the fluid inside a complex 2D network of channels and strips. More recently, there's been quite a bit of activity on the use of capillary microchannel circuits, and we have an example here on the top from the Juncker lab at McGill, where basically using microchannels that are hydrophilic, we're able to drive the flow of fluid and to implement multi-step reactions by using a sliding method to include this process. An alternative method that has been also shown in a combination of the two methods is the use of capillary-driven immunoassay (CADI) devices from the Henry Lab at Colorado State. And this is a combination of a multi-layer channel laminate with hydrophilic properties and hydrophilic coatings together with a series of pads. So it's kind of like a hybrid between the two approaches that really showed how the use of capillarity can allow you to drive fluid in a way that is not requiring external control. All of these examples use a hydrophilic surface that are used to drive the fluid flow in a porous medium and microchannel. And what is very important is that the pressure that is driving is the same pressure we were seeing before, is driven by the plus. So the flow rate is actually controlled by the contact angle and the capillary pressure. So any variation in there is really going to impact the final result of these experiments. Other effects that are more on the hydrophobic side, well, you're probably familiar with droplet microfluidics, where you have aqueous droplets in oil, and you basically have the formation and transport that are heavily impacted by the surface energy of fluids and microchannels. If you don't have the right combination of surface energies by coating of the surface or surfactants, you end up with droplets that don't form with the right size, or droplets that actually get stuck and drag onto the corners, or wetting in the channels, and kind of like mixture of between droplets, which is something that is rarely shown in papers, but is actually a big problem for whoever has worked in microfluidics, and especially in droplet microfluidics. Other examples of using hydrophobicity to drive extremely interesting functions into the system. You have here the example of the slip chip. One of the other presenters has been pioneering this technology in the lab of Rustem Ismagilov, and you can see an example here where you basically have a static droplet array between hydrophobic plates, and the use of this approach allows you to create very wide number of compartments to do, for example, digital PCR, or to do screening of multiple bacteria in parallel. More recent example coming from the Di Carlo lab at UCLA is the use of lab on a particle, where you're basically trapping fluid into a core shell, so that the droplet is actually confined by the particle, but it can also be moved around without the risk of contamination or wetting. Other examples in microfluidics that really rely on wetting, I'm just having two here, but there are many more. One is a very interesting concept that has been pioneered by Casavan and Bibi back in 2013. It's the suspended microfluidics. The liquid is actually filling by capillarity, but they're using the contact line pinning. So the fact that the liquid doesn't really like to go through corners or sharp edges, it typically gets stuck. In this way, they can do multi-step loading and control the order of filling without really having to use any external system, but just by passive control by the geometry and the contact angle. A final example I want to go into is the use of electrowetting on the electric or digital microfluidics, depending on who you listen to. This is in this case the concept is based on the use of a hydrophobic surface, and then there is a series of electrodes below the surface that with sufficient electrical power applied, induce wetting in selective areas, and you can use that to move and displace the fluid to create independent droplets, mix them together, etc. The photo here is taken from the Wheeler Lab at Toronto, but there are many other examples that you can look at by just googling this name of the EWOD or digital microfluidics. Now that we have seen some examples of microfluidic applications that do require the control of surface energy, let's look at some options on how to do this process. The first thing that I want to do is look at the properties of some native materials. You can see here a table of some examples of materials that are commonly used in microfluidics or in other applications with their corresponding contact angle. We can start here from the top with the hydrophilic section. You have a couple of examples of components that are used with very, very low contact angles, so very good for wicking and for wetting. And this is the example of glass and cellulose. As you've seen, like some of the examples before, were relying on this method, especially the lateral flow strips. Still hydrophilic, but with a slightly higher contact angle. We have gold and PMMA. I'm including this because they get used typically in academia. Mostly gold, and PMMA is a material that is coming along as a very interesting material for microfluidic devices. As we go up in contact angle, we have components that I call intermediate. So PLA, polycarbonate, COC, COP, polystyrene. Those are at the edge of between hydrophobic and hydrophilic, and they can be modified, but that's kind of like the starting range for the contact angle. And then moving on into higher contact angles, we have the hydrophobic group, where you have polypropylene, PDMS, and PTFE, or any type of like fluorinated Teflons that are hydrophobic with contact angles typically in the 3 digits. And then if you go into the higher level, lotus leaf, this is typically 160, and that's what's defined typically super hydrophobic. One thing to keep in mind is that those are reference value for static contact angles of water in air. There are typically, depending on the heterogeneity of the surface, you typically get a contact angle error which is about plus minus 3 to 5 degrees. So everything needs to be taken with a grain of salt with these numbers, especially for things that are in the intermediate, because you might have batches of materials that are slightly more hydrophilic, slightly more hydrophobic, depending on that. Whenever you're looking at the material selection, you got to think about multiple things. So one is the processing and bonding, how clean this material tends to be, and how much it tends to attract imperfections or dust or other components that might actually absorb the air or taking something from the atmosphere and change its properties. You also want to think about the surface uniformity, depending on how you're processing it. It might have some imperfections, some roughness, the things that may actually induce a higher hysteresis. Even if the contact angle is in the range you want it to be, it might actually make it a little bit harder for you to achieve the goals that you're looking for. There is also the effect of aging and exposure to the external environment. Some examples can come static electricity, contaminants. If you're using this outside and it's like a long-term application, you might actually get the effect of the UV radiation from light that can modify the properties of the plastic and then change the wetting. And then there's also to keep in mind that this is for DI water. So if you're using different fluids like water with surfactants, ionic fluids, or other components that are not DI water, this number might actually change. So you might not need to really focus only on these numbers, but take them with a grain of salt and think about the overall application. Once we have a starting point, we might not be able to achieve the contact angle that we're looking for with the native material. And so some examples of methods to change the wetting properties is the use of physical coating. So the principle here is you're using conformal coating created by physical deposition of a material. The coated material then basically covers the original surface, and then it drives the wetting performances. Some examples of this process is like a vapor deposition. You're probably familiar with parallel coating to increase hydrophobicity of microfluidic devices. You can have liquid deposition, like we use just like Aquapel is a pretty common process. It's a rain repellent for windshields that is also being used in microfluidics pretty extensively to induce hydrophobicity. You can also do spray coating or deep coating or different spaces. The key advantage here is this is a typically pretty robust method that has like a long shelf life, because as long as you optimize the process, then the coating is typically pretty stable, and it allows you for quite a bit of versatility of performances, because you do have the ability of choose different compositions and different processes. You get a little bit more variability compared to the native materials. However, in many cases you need activation, and you got to make sure that this film doesn't detach over time. You want to make sure that it's also compatible with the device geometry, especially for small features or closed channels. It might not be possible to do that with just a spray or a deep coating, because you might be losing some of the texture. And then you have to keep in mind the setup cost and the fact that it might take a while to get a repeatable and optimized process in the small versus the high volume, which is another thing we're going to look into in a few slides. Alternatively, this is a more common example. You can use surface activation. So the principle here is that you can oxidize or activate the surface with plasma, UV ozone, corona to produce hydrophilic properties. This can be used as a primer for chemical coating that we're going to see in the next slide, and or for bonding, but can also be used just to treat the surface. And a lot of you are probably familiar with this, because this is the process that is routinely used for PDMS and glass bonding. As you can see here on the right, you start from your PDMS surface that has exposed CH3 groups, and then after oxygen plasma, these become OH reactive groups that is oxidized, and this is shown into going from a non-plasma treater where the water actually beads up, to a plasma treater where the contact angle is so small you barely see any color, because the droplet really spreads out over the surface. Surface activation is a pretty good method. The key advantage here is that it's widely available. Probably every microfluidic lab has some type of plasma or UV ozone cleaner, and the setup cost for small volume is not great, is not high. However, it is a transitory effect. As you probably know, PDMS has what is called hydrophobic recovery, where over time the chain that are inside the material will tend to migrate towards the surface to get back to the original contact angle, and that can take, depending on the material, it can take the orders of hours or days. So in some cases, this is done artificially by placing the PDMS back into the oven at high temperature to regain the original properties. But if we are trying to get a hydrophilic material, you just have a certain amount of time, and then after that it probably needs to be recleaned before being used. So not ideal for scale up and high shelf life applications. As I mentioned, chemical coatings are another pretty popular set of methods for changing the surface properties. The principle here is a chemical reaction between the substrate and a precursor molecules that are typically in gas or liquid form, and then after this reaction, there is a coating that gets created on the surface, and that is permanently bonded to the original surface. Example of these are the use of plasma deposition, for example, for depositing fluorinated materials, CF4, vapor deposition, CVD or salinization is a pretty popular process, and then liquid deposition that typically can be used for silane, so for other things that are in solution rather than in gaseous form. Key advantages here is that you do get a relatively good stability or shelf life. Versatility of coatings is also a pretty good thing. However, in its activation, there is always the compatibility with the device geometry to keep in mind. It's typically harder to do deposition inside a closed channel versus an open one, because you have to ensure that the gas flow is consistent throughout a very narrow and potentially tortuous path inside the device. There is setup cost here, and then repeatability and optimization, especially for long-term stability. You end up having some potential effect here, because it gets complicated to ensure that a certain film doesn't get degraded over time. One specific case of chemical deposition is the use of self-assembled monolayers, which are a powerful tool for controlling for controlling surface energy. The principle here is that you have a reactive head group that bonds to the surface. You have a long chain, typically an alkane chain, that basically allows for stabilization because the molecules interact with themselves with hydrophobic effect and create a packed monolayer. And then the surface properties are driven by the functional group, here shown in R, which is so that you can really tailor the actual surface properties by choosing the type of reactive group depending on what you're coating to. Silents are pretty good with PDMS, glass, or other plastics. Tiols are used for gold because they react better with that surface. And then you can use the type of deposition, vapor or liquid, and then the functional group really drives the final result. So you can take a substrate that is hydrophilic and make it hydrophobic, which is something you can do with salinized glass, or you can make the opposite, where you take a PDMS which is hydrophobic, and you salinize it to make it more hydrophilic to help with bonding, or you can create a different chemical property. Advantages here is that you have a lot of versatility, as I mentioned, and then it's a relatively simple operation. The key limitation is stability. Shelf life is not that great. You typically can do, people like to use fresh coatings, especially in academia, but it's not something that can be scaled into high volume or something commercial. It needs activation, and then scalability is questionable. There are some options out there that we're going to look at later, but it's not it requires some dedicated equipment to really make sure that this can be scaled up. Now that we've seen some of the options available, I want to dig into a little bit more about the strategies when we go into high volume. So we are talking about fabricating parts and designing very innovative designs, but at the end of the day, especially in the industry side, the main goal is really to get to a point where the device itself, in order to make an impact in the world, it has to be scalable and manufacturable and can be really produced in large volumes. So the typical situation here is that we go from an in-house prototype. 10 devices a day is typically a regular number. I don't think there is much more than that, especially if you're like at the beginning of the process, because the goal here is to iterate quickly and optimize the design. And then when you go into a commercial product, you're typically looking at hundreds or tens of thousands a day. And so the amount of work that needs to be applied and the amount of the considerations there are very, very different. So as we are looking for scale up in terms of the wetting properties, the typical process for the surface property control should minimize the cost of substrate material, minimize the cost of processing and reagents, minimize the cost of quality, ensuring that the coating or the process is actually driving to what we're expecting and guaranteeing that for the customer. Allow for scalability, in this case making sure that this is compatible with higher throughput or automation. Ensure that there is adequate shelf life. Whenever a product is scaled up, you typically don't produce it right away and use it right away, so there's typically a 6 to 12 month requirements for commercial products to ensure that the properties don't change, and that's even larger for some specific applications. And then we want to make sure that it's compatible with any other steps, so reagent integration, sterilization, packaging, or other processes that are needed. So this is kind of like a larger topic, so I'm going to offer two main suggestions or two main strategies. The first strategy is try and use native materials whenever is possible. The idea here is that select a material that has the required surface properties instead of having to post-process it and having to include some extra steps. The advantages here is that you reduce the amount of steps, which means a cheaper process, reduce QC, higher chances of long shelf life, and really helping you to get the devices out to the market. Key limitation is that there might be a need for using a higher end material that might increase the cost, and then it might require different fabrication processes because it might not be the standard one, but it might require a different type of molding, a different type of bonding, etc. However, for personal experience, this is the process I would recommend whenever possible. And I can tell you the story when I was in grad school. Spent a lot of time trying to take PDMS devices or other materials and make them extremely good at being fluorinated so that I could run some droplets in there without getting wetting. And 2 years later, and many different tests with salinization and other processes, we actually ended up deciding it was much better to select a fluorinated material with the right properties and develop a new method for producing the parts and bonding them together, which is something that we have done, that I have done personally, and some other groups have shown it's possible to do. It's a non-conventional method for fabrication, but it really paid off in terms of the ability of producing devices that were giving us the right performances. Um, if it's not possible to use a native material, the recommendation is to leverage industrial system and really thinking about the selection of the material and the process based on what's available in the market. And so you gotta keep in mind the whole fabrication process, not just the coating itself, in order to make sure that this is doable. The advantage here is that you simplify the scale up, but you might end up with to pay like a higher processing cost, or having a harder transition from small to large volumes. So examples of this type of application is there are a lot of surface coating and activation processes that are compatible with roll-to-roll. In this case, there is an example of corona activation that is done in a roll-to-roll format. Deep coating is also possible. This is an example here taken from Wikipedia on the roll process. You have a roll that gets into a bath, and then the film gets created in a continuous fashion. Or in case you're looking for salinization or other processes, there are commercial systems out there that allow for big chamber with activation and exposure to the coating, the silane, so that you can scale up the overall quantities associated with it. However, in terms of like conclusions and steps, we went through introduction and basic principles. We looked at some of the wetting and capillary effect of microfluidic application, surface energy control and strategies for high volume. As I mentioned, the take-home message for me about this is try to keep the material coating as simple as possible, because every extra step costs money and ends up being complicating any type of chance of commercial success. But at the same time, if you have to do coating, if you have to do post-processing, there are plenty of options out there, and it's a matter of finding the right contacts and the right process. I want to invite you then to keep in touch. We're going to have a live Q&A session with the presenter. This is the time for the universal time. You can find your local hours by using a standard converter. If you want to learn more, and if you want to look at some of the basics of this, I would highly recommend the book from Pierre-Gilles Dejean, François Brochard, and David Queret, Capillarity and Wetting Phenomena, Drops, Bubble, Bursts, and Waves. This has been my favorite book for this type of subjects, and I've used it a lot for preparing these slides. And I love to keep in touch with you. You have my contact here, my LinkedIn, and if you have any questions, I'm looking forward to the Q&A session. Thank you so much. Bye-bye.